The primary objective of modern HVAC design is determining the exact thermal capacity required to heat and cool a building. We start by calculating the heat gained and lost through the boundaries of a specific room. This gives us the necessary volume of air to maintain comfort in that physical space, a value defined as the space load. In standard engineering nomenclature, this localized space load is represented by the lowercase variable Q. But the heating and cooling coils inside a centralized unit do not condition the room directly. They condition an airstream. The total thermodynamic burden experienced by those central coils is the system load. We represent this aggregate system load with the uppercase variable Q. In practice, uppercase Q is almost always larger than lowercase q. Accurately sizing central equipment requires measuring thermal variables that occur completely outside the walls of the occupied room. The largest of these hidden variables is the introduction of outdoor air, mandated by building codes to maintain acceptable indoor air quality. This diagram compares two common air exchange models. On the right, we have natural infiltration. On the left, mechanical ventilation. Focusing on the infiltration model, unconditioned outdoor air leaks directly into the physical space. The room itself absorbs the thermal impact of that untreated air, which increases the baseline space load. The mechanical ventilation model operates differently. A fan draws outdoor air directly into the central unit. This spares the physical room from absorbing the raw outdoor air, resulting in a lower space load. Assuming the volume of outdoor air is identical in both scenarios, the total load on the equipment is exactly the same. The equipment load remains constant, only the location of the burden shifts. Commercial systems rely on mechanical ventilation. They extract return air from the occupied spaces and combine it with a required percentage of fresh outdoor air inside the unit. This creates a blended airstream known as mixed air. The temperature and humidity of this mixed air form the starting condition for the cooling coil. Providing pressurized, safe breathing air alters the math. The central plant must process an airstream that is significantly warmer and more humid than the room it is trying to cool, pushing the system load far beyond the room's baseline needs. Most commercial buildings require more than one single monolithic thermal zone to maintain occupant comfort. Instead, a floor plate is divided into distinct thermal zones, each monitored by an independent thermostat. This introduces time-domain complexity. Due to the sun's movement, perimeters do not gain heat uniformly. Eastern zones absorb intense morning radiation, peaking by 10 a.m. As the sun travels, the burden shifts, forcing western zones to peak in late afternoon. The absolute maximum heat gain a specific room experiences at its worst individual moment is its peak load. Engineers size the terminal equipment at the zone level, the local ductwork, diffusers, and VAV boxes, strictly to accommodate this isolated peak load. Central equipment is sized using a different metric, the block load. This is the worst-case aggregate thermal gain of the entire building footprint at one single snapshot in time. Because the sun cannot occupy two places in the sky at once, it is statistically impossible for every zone to hit its isolated peak simultaneously. The system block load will always be lower than the sum of the individual room peaks. Dividing a building optimizes thermal control for the occupants, but it requires the designer to decouple the localized peak space loads from the aggregate system block load. This multi-zone configuration introduces a strict mechanical penalty when delivering minimum ventilation air. This chart highlights multi-zone ventilation requirements. Based on volume and occupants, the central unit calculates a baseline 11.7% outdoor air requirement. However, high-density spaces deviate. The interior corridor demands a 28% fraction. The space with the highest proportional requirement becomes the controlling zone. Under standard ASHRAE ventilation protocols, a centralized air handler cannot selectively distribute fresh air to a single room. It supplies a uniform mixture to the entire duct network. To ensure the corridor receives its mandated 28% outdoor air, the central unit must elevate the fresh air fraction for the entire system to 28%. Satisfying the safety code for one densely populated room forces the equipment to overventilate the rest of the building. This mathematically increases the mixed air load the central cooling coil has to process. We map airflows onto a psychrometric chart. We plot return air at 75 degrees and outdoor air at 96 degrees. Their connecting line maps the mixing, locating mixed air at 77.2 degrees. Finally, we plot the target supplied air at 57 degrees. The psychrometric chart translates raw airflow volumes into absolute energy coordinates. We can now see the exact thermodynamic distance the cooling coil must bridge. This diagram isolates sensible and latent cooling. The solid inner triangle is the space load, lowercase q. The shaded outer triangle represents the total coil load, uppercase q. The difference in their areas is the exact energy penalty imposed by outdoor ventilation air. Equipment must be rigorously right-sized to match the dimensions of this outer triangle. Overestimating the capacity carries severe operational consequences. A system with excess capacity cools the sensible heat too quickly. The thermostat shuts the unit off before it has time to ride down the vertical axis and extract the latent moisture, resulting in a cold, damp building. HVAC design requires calculating the room's heat and determining the penalty of the ventilation code, and then mapping that entire complex thermodynamic journey to precisely match the exact capacity of the central plant.